Okay, nice. Okay, cool. The thing that we'll be recording will be a Complete 30 final exam review session. So the plan for today is to solve many problems from problem set 6, but also problems from sort of the rest of the semester, which is doable because problem set 6 also contains some review questions, in case you didn't see. Before I do that, I'd just like to give you some notes about the final exam, about the final. So one very, very important note that I unfortunately have to remind you of is to make sure to practice all conversion algorithms plus other algorithms. So by other algorithms that are not conversion algorithms like CYKS. Before the final, to study for the final. So there will be a good number of questions that will sort of ask you to by hand run algorithms. So it's very important for you to remember how to do this. Honestly, if you just do 1 or 2, then it'll be good enough. This is really to sort of improve your muscle memory when it comes to running through the algorithm. Okay, so that's an important thing to note. I will also say that even though this review session will be quite heavy on problem set 6, it's it will be very useful for you to review the problems, not just from the problem set 6, but problem sets 1 to 6 are all very relevant. Plus the tutorial exercises, some of which, they weren't actually in the problem set, but I introduced extra examples or exercises, so it's important for you to consider those when studying. And the last thing is maybe the most challenging, sorry, there's some water on my screen. The most challenging part of this course might be reductions. Well, not might, it definitely is. And so in terms of reductions, please make sure to do all the reductions that were in the problem set, especially in problem set 5 and problem set 6. Okay, so these are very important for you to do. Okay, so those are general notes about the final exam. Any questions about the final at a high level? No? Okay, cool. So in that case, let's jump right into some exercises. So the way that I will do this will be to start from the sort of very beginning of the semester. So I'm going to start with some regular language kind of problem set examples. So let's do one right away. So this is going to be, oops, maybe I shouldn't do. Okay. So this is going to be from question 8 in problem set 6. There's many subparts in question 8. I haven't sort of written down each of them, but you'll recognize the question once I write it. So this first one will be to design a regular expression for the language L, but not by sort of giving a regular expression directly, but instead by converting it being an FA to a regular expression. Okay, so remember in the chapter about regular languages, we saw a bunch of different ways of representing regular languages. So we saw, DFAs, We saw NFAs. Sometimes NFAs have epsilon transitions. And we also saw regular expressions, right? And one sort of important fact or result about this chapter is that, there's conversion algorithms between each of these, right? And maybe one other thing is that, in terms of minimal representations, we only have the idea of minimal representations for DFAs. So we have this idea of minimal DFA, and we have a conversion algorithm that converts a DFA to a minimal DFA as well. So it's important to be aware of and know how to minimize DFAs as well. In this example, though, it's not really about minimizing a DFA. It's more about, converting one representation to another. So in this case, I want to create an FA representation, either an NFA or a DFA, and I want to convert it to a regular expression. So you might be wondering, well, what is the language that I actually want to design the regular expression and FA for? It's going to be the following. So the language is a set of strings over the F of AB, such that either W ends with B, or, and this is an exclusive OR, so it's very important to note that this is an exclusive OR, or the length of W is odd. Okay, so this is the language. I'm trying to see if I can turn off. Okay, that didn't seem to work. So there's an exclusive OR between these two conditions in the language. So I'm just trying to, there's like a buzzing sound, which is a bit distracting, but I'm probably not going to be able to fix it with this. Yeah, that's not helping at all. Okay, oh well. Right, so what's the strategy going to be here, right? Well, we're going to have to, analyze L, create some kind of FA for it, and then use the conversion algorithm to convert it to a regular expression, right? So let's first sort of analyze the language L, right? So what does it mean for a string to be an L? Well, let's consider the two conditions in the XOR, right? So I have, let's say this is condition C1, and this is condition C2, right? So a string is in L if and only if it satisfies C1, XOR it satisfies C2. Hopefully you remember what XOR means. It means that you satisfy one and only one of the two statements, right? So I can actually rewrite this as C1 is satisfied and C2 is not satisfied, right? Or C1 is not satisfied and C2 is satisfied, right? So then what does it mean to satisfy C1? It means that W ends with B. And what does it mean to not satisfy C2? It means that the length of the string is not odd, which means that it's even, right? So that means that W ends with B and the length of W is even, right? So this is the sort of first type of string that I kind of want to recognize. The other type of string is sort of the negation of this, which is when, or, and in this case now it's a regular disjunction, or the negation of C1. So W does not end with B, which means that W either ends with A or it's empty, right? Because the empty string doesn't end with B, or W is empty. And C2 is satisfied, in which case C2, is the length of the W is odd, right? So the length of W is odd. But then actually that means that the string being the empty string is impossible because the empty string has length 0, which is even and not odd. So that means that actually this isn't a case to consider. Okay, so this is sort of an important manipulation of the sort of logical representation of a string being in a language to something a bit more handleable by an FA, right? So why is this more handleable by an FA? Because now essentially I want to create an FA which accepts if and only if the string that I give it satisfies this, right, or satisfies this. It can't possibly satisfy both because we just went through this. It's sort of like an XOR, right? So how am I going to do this, right? Well, I'm going to create an well, let's just say an FA. I'm not going to tell you if it's an NFA or an DFA yet. And what I'm going to do is I'm going to create sort of two branches, right? One for this first possibility and another one for this second possibility. So I'm going to create an FA where I have one branch for sort of this first part and a second branch for the second part, right? So how am I going to do this? I'm going to create individual FAs and connect them together with an epsilon transition, right? I'm going to connect them together with an epsilon transition. So this means that really I have an NFA which has epsilon transitions, right? Hello, hello. Cool. So now what do these individual sort of sub-state transition diagrams, what are they going to look like? Well, the first one is going to be for recognizing a string that ends with B and is even. So if I have to check that the string is even, then that must necessarily mean that I have like a 2-bit parity checker, right? So I have two states here that go back and forth, right? So I for sure have this, right? Where this is the state that encodes strings of even length, and this is the state that encodes strings of odd length, right? And at some point, right, I need to accept the string, and I'm only going to accept the string if I finish with a B, right? So now, can anyone tell me whether I should finish with a B from here or from here? From the odds, right? Why the odd? Because I have an odd number of letters so far, plus the B, odd plus 1 is even, right? Which is what I want. Nice, thank you very much. Excellent, so that means that I exit from the odd, and then I accept, right? So this ensures that I only go to an accept if I ended with B, and the fact that I'm coming out of the odd means that, you know, I had an odd number of letters so far, plus the B means I have an even number, right? Which is what I want to satisfy here. Nice, cool. So hopefully that's okay with everyone. For the sort of second branch, it's going to be the same idea, right? Same idea. So I'm going to loop back and forth, right? Again, this encodes strings of even length, and this encodes strings of odd length. But now I want to end with A, right? So the thing that's going to come out is going to have a label A. And I want the string to have length odd. So then the argument is symmetric, but just sort of on the different state, right? So instead of coming out of odd and then having A and then being even, you come out of even, then with the A, you're now odd, right? So that's what I'm going to do. I'm going to come out of here with an A, and then I'm going to go to an accept state. Okay? And now this is the NFA. It's on NFA. I'm sure you could have thought of, maybe many of you have thought of different ones, but this is one that works, in my humble opinion. Nice, cool. So is this okay with everyone? Nice, some nods, good. You can. I'm not particularly interested in being super efficient with my states right now. Yeah, it's also more difficult to present a solution that's super efficient. Yeah, but yes, you can. Yes, you can. Okay, so now I want to convert this to a regular expression, right? So I want to convert this. Now I want to convert, let's call this M to a regular expression, right? And so how am I going to do this? I'm going to remind you of the state reduction algorithm. You can also use the algorithm presented to you in class, but to be honest, I don't understand it, so I'm not going to do that. You should never present something that you don't understand. So let's take the machine M and let's state reduce it. So as a reminder, how do I run the state reduction algorithm, right? Well, the goal to keep in mind when I run the state reduction algorithm is that I want to get to an FA that looks something like this, right? Where R is some regular expression, because then if this is an FAM, then of course the regular expression that's equivalent to M is R. So that's what I want to do. So then if you recall, the first step in the state reduction algorithm is ensuring that I have a single start state and a single accept state, and making sure that the accept states and the start states are different, right? Which is kind of what I have. So I have a single start state, but I have two accept states. I mean, the nice thing is that the start state is not an accept state, so there's no extra work to be done there. But there is a problem because I have two accept states, right? So what I can do to just have one is, use my nifty epsilon transition, connect these two to a single accept state, and make these regular states. Okay, so this is the first step. Nice. Then remember the whole spiel behind the state reduction algorithm, also sometimes called the state elimination algorithm, is to eliminate states. So you want to eliminate states in such a way that you preserve the logic of the machine. And to do that, you're essentially going to use regular expressions as the labels to the edges of the FA. So I'm going to do this for a few states at the same time, just to save a bit of time. So I'm going to delete this state, right? When I delete a state, I have to make sure that I'm preserving the logic by sort of adding additional transitions. So if I delete the state, then what do I have to sort of add back to my slightly reduced machine? Well, I have to add a self loop with A or B and then A or B, because this sort of part of the machine is allowing me to self loop on this state. Right, so that's what I'm going to do for that. And let me actually write that immediately. So let me copy this. Let me do that. So I'm going to delete the state. Okay, I was going to do multiple at once, but maybe it's just safer to do one at a time. Okay, so I have this. Then the other thing that I will eliminate, I mean, feel free to use whatever order you want, but my sort of intuition tells me that it might be nice to eliminate this one next, right? So if I eliminate this state next, then I have to consider the fact that I can use this state to go from here to here, right? And I can also use this state to self loop on this state, right? So that means that I have to add. So if I eliminate this state, right? Then let's see if I remember. I have a self loop A plus B, and then I have an edge that goes to this other state with A plus B, and then B, right? Okay. So hopefully everyone's with me so far. Now I'm going to rush things a little bit, because essentially now I can see that really what's going on is I have essentially two paths to the accept state, which makes sense because the two paths are like the two types of strings that my machine will accept. So then I'm just going to notice that, the two paths are essentially, there's the top path to go to the accept state, and there's the bottom path to go to the accept state. And those top and bottom paths are going to be, get out of the way, thanks very much. They're going to be, the epsilon transition, then A plus B, any number of times, which is just A plus B star, right? Then A plus B, and then epsilon, right? So that's going to be the top path. So epsilon, A plus B whole star, then A plus B, and then epsilon. And then the bottom path is, epsilon, then A plus B, any number of times, so star here, then an A, and then epsilon. So then that's going to be epsilon, A plus B whole star, then an A, and then epsilon, right? Okay. And now I can get rid of the epsilons in the regular expression, because, if I have a regular expression A epsilon, then it's equivalent to just the regular expression A, right? So I'm going to get rid of these guys here. And then, you know, I can just join this into a single, whoopsies, I can join this into a single edge by just having an OR between them, right? Because this is like, it's like a logical OR, right? Either I can take this path, or, and the OR in regular expression logic is plus, or I can take this path, right? So then that means that the final machine I will have will be, let me just call this R1 and R2. It will be R1 plus R2, right? So then the final regular expression R is going to be, let's see, A plus B whole star, then A plus B, B, or A plus B whole star, and then A, right? And if we remember, I'm just going to quickly scroll up, don't worry, I'll come back down. If we remember what the initial language was, I'll show you why this kind of makes sense. So the initial language was, you know, L is a set of strings where either the string ends with B or XOR, right? The string is of even length. So if the string ends with B, or sorry, of odd length. So if the string ends with B, then I have pairs of A's and B's, and then I have an extra A plus B, B. So then this is even, right? This is even and it ends with B. Or if I sort of end with A, then it's because I'm odd, right? Because, you know, I have pairs of A plus B's, right? So I always increment by plus 2. And then I have an extra plus 1. So I have something like 2n plus 1, right? Which is odd, right? So then this makes sense. You know, maybe you could have thought of this directly. I'm sure that's possible, but we got to do what the question tells us to do. So and that's what we did. Nice. All right. Any questions about this? No questions. All right, cool. So let's move on to another exercise. This one is, again, going to be from set 6. So from set 6, question 8. Except that now it's going to be, we're going to sort of go up one level in the Chomsky hierarchy. We're going to talk about context-free languages, right? So just a quick reminder, you know, you have regular languages. Not all languages are regular, so some of them are outside here and are context-free. To sort of formally show that a language is context-free but not regular, you need to use the pumping lemma for regular languages, right? So that allows you to say that you're outside of reg. And then what allows you to say that you're inside CF is either, you know, L is inside CF if you can find a PDA P such that L of P is equal to L, or in fact, this is sort of like an if and only if, or you can find a context-free grammar G such that L of G is equal to L, right? And again, like in reg, there are conversion algorithms from one to the other. So please be aware of those conversion algorithms. And then the other thing that you talked about in the sort of chapter about context-free languages was the idea of, you know, parsing, right? So parsing and parse trees. And remember, when you talk about parsing and parse trees, you always want to deal with grammars that are in Chomsky normal form, because then you have binary trees. Once you have binary trees, you can also do parsing. You can check in cubic time whether a string is or is not in the language generated by G, and you do that with the CYKS algorithm. So don't forget how to run these conversion and parsing algorithms. And we're, to sort of help you not forget, we're going to do an exercise where we remember. And so what is that exercise going to be? It's essentially going to ask us to provide a context-free grammar in Chomsky normal form for the following language, where the language is going to be ANBM, where N and M are greater or equal to 0. And in this case, this is a disjunction, but I mean, really, anyways, either N is strictly greater than M, or m is equal to 3n, right? So a language, or sorry, a string is in L, if and only if, for instance, it looks something like, I don't know, A7, B5, right? Because here the number of A's is strictly greater than the number of B's, right? Or it might be that you have maybe A3, B9, which is fine because the number of B's is 3 times the number of A's. So these are the two possibilities. Okay, I mean, these are two particular examples, right? It's not the only two. The language L is not a size 2. Okay, and so how are we going to do this? Because the annoying thing about this question is that it asks for the context-free grammar to be in CNF, right? So it'd be kind of hard to think of a grammar in CNF directly, right? I think for regular expressions, it's kind of doable. CNF directly, it's a bit harder. But that's not a big deal, right? Because what we can do is we can just create a context-free grammar G such that L of G is equal to L. And then we can just convert G to CNF using our nice conversion algorithm, right? Okay, so let me give you some time to think about it. My annoying habit is to do this. Sorry about that. Let me give you 2 minutes. So try to think of what the context-free grammar would be, and if you get there, to convert it to CNF. I'll give you 2 minutes. All right. That tells me time is up, but feel free to continue it if you want. You can just check the answer as I go. So, okay, remember what I said before. We want to create first just a general context-free grammar and then convert it. That's going to be a bit easier than directly doing it. So the general trick whenever you have a language that has an or between two conditions is just to create sort of two kind of intermediary start variables, right? One that generates strings for the first condition and another one for the second. If there's sort of redundancy, it doesn't really matter because it's not an XOR, right? So I don't care, right? So let's see, how am I going to do that? I'm going to say, my global start variable is going to go to two intermediate start variables. This one is going to be for n strictly greater than m, and this one is going to be for m is equal to 3n. And just a reminder, we're dealing with ANBM here. Okay, so then let's do S1 first, right? So what is S1 going to look like? I essentially want to generate strings where I have more A's than B's, right? So if I have like an example string, maybe AAA, BB, right? How do I ensure that, you know, this is generated by my context-free grammar? I can essentially generate A's and B's together, right, in pairs, until at some point I sort of run out of B's to match with A's, which must happen if I do actually have a string that I'm generating in the language. And once that does happen, I just generate the remaining extra A's, right? So what does this look like? You know, at first, I generate the A's and B's together, right? At some point, I'm going to run out of B's to match with A's, at which point I'm going to sort of switch to just converting, to just generating a bunch of extra A's, right? So from the variable A, I'm going to generate a bunch of A's. And it's important in sort of the base case here to not have the empty string. If I had the empty string, then this would mean that n was greater or equal to m, right? But I want strictly greater. So then I'm going to have that the base case for A is just I generate a single A, right? So I at least have one extra A over the number of B's, okay? All right, so that's for the first sort of part of the language. The second part is when m is equal to 3n. So I'm going to generate that from S2. Now, what's an example string? Like I said, maybe, let's see, I don't know, AA and then B, so B6. So how am I going to ensure that, you know, for every A, I have 3 Bs? Well, literally just like operationalizing what I just said verbally, right? So for every A that I have, for every A that I place 3 Bs to the right, right? And I just do this over and over again until I get to the end, in which case at which time I'll generate the empty string. Yeah, so many prepositions to choose from. Okay, so I generate an A on the left, and then 3 B's on the right. And I sort of keep recursing on S2, right? Eventually, I have to terminate, and my base case is just the empty string. That also kind of makes sense because, you know, A0, B0, which is the empty string, you know, for sure, 0 is equal to 3 times 0, so that's valid, right? So that's a valid that's a valid base case, right? Okay, and so this is a context-free grammar, right? Maybe you thought of a different one, but this is the one I'm going to go with for the conversion algorithm. Okay, is everyone still with me? Yes, some nods. Good, thanks. So now let's convert this to CNF. Let's call this G to CNF, right? And so as a reminder, how do I convert things to CNF? I first, and the order, right? The order is very important. I'm not just telling you this sequence in sort of an arbitrary fashion. This order is very important. So it's very important to start by removing the epsilon productions. And then to remove the unit productions. Right, you do 1 before 2 because removing epsilon productions might introduce new unit productions, right? So then you remove the unit productions. Then you remove the non-generating variables. So variables that, you know, you can't get rid of intermediate variables when you're deriving strings. And then finally, you remove unreachable variables. So variables that cannot be reached from the star variable S here, okay? And again, it's important to do 3 before 4 because once you remove non-generating variables, you might introduce more unreachability, right? So that's why this order was chosen for a particular reason. Okay, cool. So let's try to do this on G. Copy. So let's first remove epsilon productions. So do I have any epsilon productions in G? Yes, I have one, right? It's this one, right? So if I want to remove the epsilon production rule, then I have to account for every sort of place that I could replace S2 with the empty string, right? And in this case, there's two such cases. There's this case here where at some point I'm going to eventually replace S2 with the empty string. So, I add the production rule where I would have replaced S2 with the empty string. So that would be, A empty string B, B, B. But then that's just A, B cube, right? Then there's another instance where I would replace S2 with the empty string. That's here, right? But in this case, right, I don't want to remove S2 and replace it with epsilon. Why? It wouldn't work because I would add back an epsilon production rule. The exact thing I was trying to remove. So that would be unsuccessful. And then I would be in an infinite loop probably. So very important, right? If you have a single variable that is nullable, right, it can be replaced by the empty string. Don't replace it by the empty string, right? So leave it intact. Okay, but just FYI, as a result, right? As a result, that means that the sort of grammar, so the grammar G prime in CNF is actually not going to be able to generate the empty string, which is fine because I'm explicitly asking to convert it to CNF. So that's within the constraints of the question. Okay, so I removed the epsilon production rules. Nice. Now, the next thing I need to do is I need to remove the unit productions. Unit productions. So let's copy this grammar. And let's paste it. So let's erase this guy. And now let's see which of these guys are unit production. So I have a couple, right? I have this one, and let's see, also this one. So what I probably need to account for is, S going to S1, S going to S2, S1 going to A, and also S going to A, right? So don't forget this sort of intermediate one where, I also want to add the productions for A because S can go to A by sort of jumping through two production rules, okay? So with this in mind, right, I'm going to take the grammar and delete the unit productions that I have, right? And now I just have to sort of heal this deletion by adding back all the production rules of, S1, S2, and A to the sort of corresponding places. So for S, I have to add the production rules for S1, S2, and A. So that's going to be, A, S1B, AA, and A, and also A, S2, B, 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 and A, B, 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 right? And then right, so that does it for S, right? Then for S1, I just have to add the production rules for A, right? So then I add the production rules for A, which is AA and A. Okay. Now my grammar does not have any unit productions, right? So that's nice. Now, the next thing I need to do is I need to check for non-generating variables. So let's copy the grammar again. And let's put this down here now that I have more space. Okay. So remember, a variable is non-generating if and only if there is no way to sort of generate only a string of terminals from that variable, right? But here I can generate a string of terminals. Here I also can. Here I also can. And here I also can, right? So I don't have any non-generating variables, right? So no non-generating variables, which is nice. I just keep the grammar as is, right? What about unreachable, right? Unreachable variables. So let's see if we sort of create a sort of reachability graph, whether I can reach all of the variables from S. So if I start from S, I can go to S1. I can also go to A, and I can also go to S2, right? So yes, all the variables are reachable. So no unreachable variables to delete. Delete. Very nice. Okay, that's good. It's also a good sanity check for your original context-free grammar, because if in your original context-free grammar you had introduced some kind of unreachability, then it's probably because some part of your logic was off, right? Because normally all of the variables that you're using should be useful for something, right? But if they're unreachable, then they're not very useful. Cool. So this grammar is simplified, quote unquote. It's not much simpler than before. But it's definitely not in CNF, right? In CNF yet, right? Because it's not binarized. So the last thing I need to do is I need to actually convert to CNF, right? And so how am I going to do this? I need to, first of all, introduce sort of terminal variables. So TA gives you A, and the terminal variable B gives you B, right? And then I have to binarize all the production rules, right? So I have to binarize. And to do this, I'm going to use the nice trick of, if I have something like, I don't know, S gives me X, Y, Z, then I can binarize this by saying, it's the same as S gives me X, X1, and X1 gives me YZ, right? So I do this sort of creation of new sort of intermediate variables. Okay, so this is going to take a bit of work, right? But it's okay. Let's first replace all the variables, all the terminals, sorry, by their corresponding terminating variables. So A, wherever you see A, I'm going to write TA. And I'm not going to copy it just because I'm a bit lazy. So then I get something like this. Okay, so this is my grammar now with a bunch of terminating variables. Still not in CNF because I have a bunch of production rules of length strictly greater than 2. So I have to get rid of those. Let's see. So to do that, I'm going to start by sort of binarizing this guy, TA S1B, right? So to binarize TA S1B, TB, sorry, I'm going to introduce a new sort of intermediate variable x1. So I'm going to have, x1 gives me S1 TB. I'm realizing it actually might have been better to copy the grammar, so let me do that. Okay, so I'm going to copy this. I'm going to put it here. And then this new intermediate variable is going to be here, right? Now I'm going to replace it wherever I see it in the grammar. So it's here. And it's here. And that's it, right? Nice. Cool. The next one I will do will be this TA TB 3 times, right? So to do that, if I have TA and then TB 3 times, what I'll do is I'll create x2 for TB 3 times, and then really x3 for TB twice, so that then I can just replace this with x3. Right, so then these are the two new production rules that I have. And now the thing is, wherever I see 3 TBs, I can just replace it with x2, right? Because then x2, I can get, TB and then x3, and then x3, I can get TB and then TB. So then effectively, I'm sort of having x2 gives me TB 3 times, right? So let's do that. I'm going to replace TB 3 times here. I'm also going to do it here. And here. And here. Nice, very nice. I'm almost done, right? The last thing that I need to get rid of is this guy, right? This is still like 3 variables. So I just have to binarize this one, right? And so to do that, I'm going to introduce another new variable for S2x1, S2x2, right? So let's see, x4 is S2x2. So this is going to be replaced here. And this is going to be replaced here. Okay. And now, very nice, I have, let's see, all my variables go to binary, except I mean get S goes to A, but that's fine because CNF allows, single terminating letter variables. So yeah, seems good. Nice. Yes, that's true. So, okay, so then that's a good point. The point is, what about the empty string? So then this grammar is, G prime is in CNF. But now the problem is, L of G prime is the same as L of G, but minus the empty string. So, I mean, it depends on the question, right? If the question says, ignore the fact that you lose the empty string, then you can just leave it like this. If it doesn't, then you should probably also add an empty string production rule here. Right? Okay. Yeah. Yes, but then it's not in CNF, right? So it depends, right? Right. So this is only if required, right? So it might be in the question it says, convert it to CNF and keep the fact that you have the empty string, right? So it's possible, but yeah. Okay. So I will let people finish copying because this was a lot of writing. Yeah, question, yeah.
Instead of like adding an A, add it all into S1. Like the so but like
I have to think about this. Let me show it to me after, and then
is it better to have fewer variables or like
okay. So the question was, is it better to have fewer or more variables? It's up to you. Whatever makes the grammar the easiest to understand for you. So there's absolutely no preference. I mean, yes, if you have more variables, then of course you're going to have more work to do in converting it to CNF. Yes. Yes. But it's really up to you. Okay, so it looks like people are good with writing down. Yeah? Okay, cool. So let's move on to another question now about language classification. So we're going to now have some language classification questions. So language classification questions are a classic type of question to give in 330 final exams. Essentially, you're presented with a language L, and then you're asked, is it regular? Is it not regular but context free? Or is it not even context free? Right? So if you claim that the language is regular, essentially what you're claiming is that you need a finite amount of memory to recognize it, right? So as a reminder, things that usually require a finite amount of memory are things like, things that have modulos, right? So things that have modulos typically only finite memory because if you just create a cycle, then you sort of represented the, maybe in this case, modulo 4 thing, right? The other thing that's typically only sort of requiring a finite amount of memory is a question of like, is V a substring of W? So here I'm abusing notation where belongs to means a substring. So this again is kind of only requiring a finite amount of memory, finite number of states, because you just have to wait and see if you see V. If you do, then you go to an accept state, right? But V, the string is finite, right? We're always assuming that strings are finite. So then you only need a finite number of states, okay? So things like this typically are sort of regular, right? Because you can create sort of closed finite state transition diagrams for them, okay? Things that are not regular but context-free. So almost by sort of definition, if you're not regular, then you can't design a finite FA, which means that if you actually had to design an FA, then it would require an infinite number of states, right? So you need some kind of infinite unbounded memory. To recognize the language, right? Which is kind of a problem, but because you're claiming that it's context-free, it's maybe not such a big problem because you can use a single stack as the memory, right? But it can be handled by a single stack memory, right? And so just a reminder, what are the sorts of things that you can do with stacks, right? So you can use a stack as kind of like a counter, right? So that's why, for instance, you could use a PDA to recognize A and Bn, because you can use the stack as the counter for the A's, right? And then once you start reading the B's, you can check that the number of B's matches the counter, right? However, you can't use the stack as sort of multiple counters, right? So that's kind of why you can't recognize A and B and Cn with a stack, because you would really need two stacks, right? You need to first count the number of A's, check that it's the same as the number of B's, and then also count the number of B's and check that it's the same as the number of C's, right? So you need two stacks, right? Which is not what you kind of have. So that's sort of one thing that you can and cannot do with a stack. Another thing that's kind of nice with stacks is that you can recognize sort of, or you can recognize that things that have to do with reversing the string, right? So in a stack, right, when you're sort of reading a string, if you read the string and you push it onto the stack, then effectively what you're doing is you're sort of reversing the string, right? Because you push from left to right, so the leftmost part of the string is at the bottom of the stack, and the topmost part of, or the rightmost part of the string is at the topmost part of the stack. So then, if you read it from top to bottom, then you sort of reverse the string effectively, right? So that's why you can recognize stuff like W reverse, or W is equal to W reverse, right? But then you can't do something, right? You can't do something like, so this is good, this is not good. You can't do something like recognizing the copy or the duplicate of the string. So WW, because this kind of requires two stacks in the sense that you need to sort of track where the middle is and sort of use the two stacks as sort of the infinite tape that we use in the Turing machine. Okay? So this just doesn't work because there's sort of no reversing involved. No reverse involved, which typically sort of should tell you that you can't do this with the PDA. Okay, and then finally, if something is not context-free at all, right? If something is not context-free at all, then I mean it's basically what I just said. You essentially need at least two stacks. So A and Bn, Cn, WW, and so on. Okay. And so then That's great for like intuition and for like, you look at a language and you want to make a decision quickly. This is great heuristics. But then you can't just write this in a final. Please don't do that. When you do this decision in a final, you have to be a bit more sort of rigorous in your answer. So if you claim that something is regular, then you must give some kind of representation for the language. So either a regular expression or an FA. If it's context-free, then if it's context-free and not regular, then this requires two answers, right? First, you need to show that it's not regular. So you have to give a pumping lemma for regular languages argument, or a closure property argument, right? So this is the first part of the solution. The second part is then to argue that it's context-free. So you either give a context-free grammar which generates it, or a PDA that accepts it. Okay. And then if you're claiming that it's kind of even outside the realm of context-free languages, then you have no choice but to give a pumping lemma argument for context-free languages. You can also or sometimes you use both, sometimes you only use one, or you use the closure properties for context-free languages. Okay, so this is the general way to approach these problems. Okay, make sense? This is just a review. Hopefully people remember this. Now let's look at a few exercises about this. I'm going to scroll. Okay, so let me write the first exercise. So the first exercise is, classify L, where, classify L means whatever I just said it meant. And here L is 0, 1, N, 1, 0, M. So a bunch of 0, 1s followed by a bunch of 1, 0s, where N and M are greater or equal to 0, and N plus M is odd. Okay, so again, I'm going to be annoying and ask you to think about it. I'll give you 2 minutes. On this question in general, but is it still correct classification or? I mean, you're given a disjoint choice, so then that would never happen. Yeah. Alrighty. So hopefully you had a chance to think about it. Let's look at it together. So the language here that we have is like I said before, a sequence of zeros and ones, right? So a bunch of zeros and ones, followed by a sequence of ones and zeros. So already, if the language was just that, then it would be regular, right? Why would it be regular if it was just that? Because, you know, I could just have the regular expression 0, 1 star, 1, 0 star, right? And that would recognize all the strings that look like this, okay? Maybe if we look at the condition, it's going to make us not regular. So let's see what the condition is. N is greater or equal to m, n and m is greater or equal to 0, so that's fine. And n plus m is odd, okay? So n plus m is odd. That's actually not going to be so bad because really what this is saying is I just have to consider a few more specific cases, right? Because I mean, in theory, right, or in practice, n and m are, you know, two integers, right? And so just by the property of being an integer, well, n will maybe be even and m will maybe be even, right? But then there are other possibilities. Maybe n is odd and m is even. Maybe n is even and m is odd. Or maybe they're both odd, right? This analysis is useful in this case because we see that if we sum these things, right? If you sum an even number with an even number, right? That's still an even number. So then that doesn't fall within the sort of cases in our language. If you have an odd number like 3 and another odd number like 5, if you sum them together, sum them together, you get 8, which is even. So then this also doesn't help. But the two cases that are actually positive cases are these two, right? So if I have an odd number and an even number, together that remains odd. And the same thing if, you know, it's the other way, right? So that means that really what this is saying is it's just saying be a bit more careful in terms of the languages you recognize with respect to this regular expression, right? Because, you know, this is going to lead to odd sums and so is this, right? So that means that I just have to sort of hard code both of these cases, right? So when n is odd and when m is even, what does this mean? It means that, you know, I have a bunch of zeros and ones, right? And these zeros and ones can be seen to be in kind of like pairs, right? But because I have an odd number of them, I always have like an extra one after the sort of pairs, right? So I can represent this with a regular expression. I can just say, you know, the zeros and ones are always in pairs. And then I have an extra 0 and 1 to make it odd, right? And then for the ones and zeros, well, the ones and zeros, they're always in pairs. And there's never anything extra, right? So they're always in pairs because that sort of makes them always even, right? And I never have this extra thing that I was talking about here because that would make it odd, right? So then I have this sort of sub-regular expression for this case, right? And now I have another case, right, which is very similar, except that it's just that I have, you know, even for here and then odd for this. So then it would be, you know, 0, 1, 0, 1 whole star, and then 1, 0, 1, 0 whole star, and then the 1, 0 to make it odd, right? And then this is a regular expression that describes the language, which makes the language regular. You could have also given an FA, which I did somewhere in these papers, but it gets a bit messy. Regular expression is quite clean. Okay, cool. Nice. All right. So that one's not bad, right? Let's look at another example. So the question is the same. Classify L. Now in this case, L is going to be 0n, 1m plus n, 0m, where again n and m are greater or equal to 0, and n plus m is odd. Okay. All right. So again, I will give you some time to think about it. All right. So hopefully, I mean, that wasn't a lot of time, granted, but hopefully you thought about it a little bit. So to be honest, this is a very classic way of representing strings in a way that's supposed to kind of like trip up some students. Essentially, what you kind of need to notice is that if you take the string 0 power n, 1 power m plus n, 0 power m, right? This might be a bit like tricky or like, oh, can I even do this with a single stack? Because I have to like remember the n and then the m and then match the n with the n, and then it's kind of weird. But really, you have to sort of notice that this m plus m is how many ones I have, right? So then, if I have, m plus n ones, right? Well, I also have n plus m ones, right? So this is just sort of a commutativity thing, right? So then this is actually equal to 0n, 1n, 1m, 0m. And then maybe this is a bit more helpful to sort of analyze because, for sure this can't be regular because I have something like count the number of zeros and then check them with the number of ones. The fact that, n plus m is odd doesn't really help reduce the difficulty of this, right? Because I still need a counter, right? Which I don't have with the regular language. But I can use a stack, right? Because, I can count the number of zeros, check them with the number of ones, then I reset my counter to 0. Once I'm here, I count the number of ones, check them with the number of zeros, right? And it doesn't really matter that n plus m is odd. It just means that I have to be a bit more careful in terms of like, what do I sort of consider when I'm reading the first batch of zeros, and what do I consider when I am reading the second batch of ones, right? So essentially, this is just going to cause me to restrict my cases again, where n should be odd and m is even. Or, right, so this part, so this is okay with a stack, right? But it's not okay with an FA. And then this part just sort of causes me to filter the strings a little bit more. And filtering the strings based on like modularity of length, that's always something that I can just do with like a state transition. So then, I use the state transition and the stack together. That's a PDA, so I have something that's contextual, right? So n is even. Okay, so that's great intuitive argument. Definitely not a solution in a final exam. For a final exam, I first have to give a Pompey lemma argument and then a either a context-free grammar or a PDA, right? So let's first argue. So first of all, L is not regular, right? Let's use the pumping lemma for regular languages to argue this. And so to do this, I'm going to say, remember how I like to present and do the pumping lemma. I do this as a game between the for all and the existential. The for all is my opponent, and I play the existential. My goal is to defeat the for all player, right? So we always start the game with the for all player. The for all player picks a p in the set of natural numbers, right? That's their move. I have no idea what p is, right? My move is now to pick some string in L such that some string in L, right, such that that string is of length at least p, right? There's an infinite number of strings that I could pick that sort of satisfy this condition. The other condition I kind of have to think about when I'm doing this is if I think, a few moves ahead, is the string that I'm dealing with easily pumpable sort of outside of the language? That's what I have to think about, okay? One sort of classic string to always try is something like APBP, right? So that was the classic way to show that ANBN was not regular. So you kind of want to always start with something like that if you have a language that's kind of like some constraints on the number of letters in the language. Okay, so let's just remind ourselves, mostly me, what the language actually is. Oops, that's not that. And let's see if we can find a good candidate string, right? So, I mean, one obvious choice might be, can I just do 0, W is equal to 0p, 1p, right? Can I do this? I can. I'm suspicious that I can, right? Because I need this string to always be an L, right? But then is this always going to be an L? Not necessarily, right? Why? Because I have 0p, 1p, 1, 0, 0, 0, right? So, what if p is even, right? If p is even, then p plus 0 is still even. And so then my string is not in L to begin with. Yeah, that's not good, right? My string should work for any p, right? So that's why I'm playing against the for all player, because my strategy should work for any p. And I can't know ahead of time what the p is, right? So then, okay, let's see. Can we fix this issue by just saying, let's do W is 0p, 1p, 1 to the 1, 0 to the 1, right? So this is going to fix the issue. Well, if I have this, okay, maybe not, right? If I have this, then, m is 1, and n is p. So then n plus m, that's p plus 1. So then that's great if p was even, right? But now what if p is odd? Then, odd plus 1, that's even. So then I'm no longer in L anymore again. So then the opponent wins. Sad. Okay. So that also doesn't work. So now what I need to do is I need to be a bit more clever. I need to pick a string where it doesn't matter whatever p is. I'm going to have this kind of string, and this constraint is going to be respected. Well, what do I know about an integer being odd? I know that an integer is odd when I have something like 2n plus 1, right? So, I mean, what if, I did something like, 0 is to the power of 2p, 1 is to the power of 2p, and then I have 1 to the 1, 0 to the 1. Then this is going to work, right? Because n is 2p, m is 1, and then n plus m, that's 2p plus 1, which is always odd, right? Whatever p is. So this is going to be the string that I'm going to pick. You could have picked a different one, but this is the one I'm going with. Okay? Nice. So now that's a string I pick. And, for sure, the length of W is, 4p plus 2. So this is greater or equal to p. Always make sure to check. Now it's the opponent's turn. What does the opponent do? Well, they decompose the string, right? They decompose the string, and they want to do this such that I can't find a pump, right? So they're going to decompose W into X, Y, Z, such that XY has length at most P, and Y has length at least 1, right? These are the rules that the for all opponent has to abide by. And that's kind of nice that they have to abide by these rules, because then I know what actually Y is going to be, right? Because if W is, a bunch of zeros, and then a bunch of ones, and then an extra 1, and then an extra 0, right? And I have, 2p zeros, right? And because the decomposition is, x, y, z, where the length of xy is at most p, then xy is at most here, right? Maybe this is the middle of 0 power 2p, so maybe this is where I get to p. So then that means that, I have, x, and then y, and then the rest of the string is z, right? So then that means that my string y, I know for certain, whatever the for all player picks, I know for certain that it's going to be 0 power k, where k is at most p and at least 1, right? It's at least 1 because of this, and it's at most p because of this, right? Okay, and so this is sort of, I mean, the for all players move ends really here. This is just my analysis of the for all players move. So now it's back to being my turn. At my turn, right, what do I need to do? I need to find an I such that Wi, which is going to be x, y, I, z, is not in L, right? So you have to sort of think of the I as, how many times am I injecting the Y into the original string. So if I is 2, then W2 is X, Y, Y, Z, right? So I'm adding one extra Y to my string, right? So that means that I would take this Y and I would add an extra one here. And it turns out that's going to already be good enough. Why is this going to be good enough? Because if I pick W2 and I inject, this Y into my 0 power 2p, then W2 is going to be 0 power 2p plus k, 1 power 2p, 1 power 1, and then 0 power 1, right? And remember, the string, for it to be in the language, has to be something like 0n, 1, n, 0m, no, yeah, 1m, 0m, where n plus m is odd, right? But then I don't have this, right? Because if I analyze this string using sort of the n and m here, then it looks like this tells me that n is 2p plus k, and this tells me that m is 1. So then the sum here of n plus m looks, it is 2p plus 1, but then this is not the same as the n that I've the n and m that I've analyzed, right, which is 2p plus k plus 1, right? In fact, this is strictly greater, right, because k is at least 1, right? So that means I just have a string that doesn't work within the constraints of this language L here, right? So W2 is not in L, which implies that L is not regular. Okay? Because all I need to do at the last step is to find a particular I such that W2, so this pumped string, is not in L. Okay? Good? Nice. All right. So that's nice, but that's only half of the solution. Sadly, this is a long one. We also have to show that this is context-free, right? So let's see. How are we going to show that this is context-free? Let's do a grammar. Okay. Just letting you finalize. I'm going to scroll down a little bit. Okay. All right. Okay, so now I also need to show that L is context-free. And a reminder, L is 0n, 1n, 1m, 0m, and n plus m is odd. Like I said before, this thing about n plus m being odd just means that I have to have like 2 cases, right? So I need the case where n is odd and m is even, and the other case where n is even and m is odd. Okay, so I'm going to use S1 for this and then S2 for this. So I'm going to have S gives me S1 or S2. And then S1, right, what does S1 have to generate? It has to generate something like 0 to the power of odd, 1 to the power odd, and then 1 to the power even, and then 0 to the power even, right? So I'm just going to create variables for each of these kind of things, right? So I'm going to have A0 for this thing, and B even for this thing. Okay. So A0, what is this going to look like, right? So finally, we're at the actual case of generating strings. So A0 is just going to be, a bunch of zeros, right? A bunch of zeros, and then a bunch of ones, where these zeros are sort of odd, and these ones are odd, and there's the same number. So if there's the same number, then for sure I need to do a matching, right? And then if they're odd, then what I can do is I can do, generate a pair of zeros for a pair of ones. And at the end, the base case is just going to be I have 0, 1, right? So I'm going to generate 2 zeros on the left and 2 ones on the right, right? So that's going to keep my parity the same. And the base case is just I have odd parity, right? So, you know, if I start from the base case, I have odd parities, and then I'm adding pairs of zeros and ones to the left and right, so I'm keeping my odd parity the same, right? And this is going to be A0. And then really the rest of all the other production rules are going to be the same logic. So BE, it's going to be producing ones in pairs with zeros, and then ending with the empty string, because you know the empty string has 0 ones and 0 even, 0 zeros, and 0 is even, right? So then it's all good. And then I'm just adding pairs of ones and zeros together. So that respects the parity of keeping from the base case staying even when I'm recursing, right? So that's going to be for S1, right? Then for S2, I need to generate what? I need to generate something like 0 even, 1 even, and then 0 odd, 1 odd. Okay, so then the logic is going to be very, very similar, right? I'm going to call something, this first thing A even, and then the second thing B odd, right? And then A even, that's going to be, you know, generating zeros and ones, but now in pairs. So it's going to be the same thing as this guy, except that my base case is going to be the empty string, right? So I'm going to end with the empty string. And then B odd, you know, it's going to be the same thing, generating pairs of zeros and ones, but then the base case is I have 0, 1, because then I have an odd parity. Okay. And then this is a context-free grammar that would work. Yeah? Is there a mistake? Yes, yes. Thank you very much. Thanks very much. Yes. Very good catch. So this would be 1, 1, 0, 0. Why? Because, you know, B0 is for, oh, I see. Oh, it's just because I started with the, okay. Thank you very much. Right. Right, because remember the language is zeros, ones, ones, and 0. Okay, cool. Nice. So this is a context-free grammar. Yeah, you could have also done a PDA. I'm not going to do it because my hand is getting tired. But to do a PDA, the general logic would have been, you know, I have maybe 2 branches. So this one is for n odd, and this is m even. And this one is for n even, and this one is for m odd. Right, and then what I need to do is I need to sort of count. So I'm going to sort of count the number of zeros and match them with a number of ones. But I have to ensure that I have an odd number of zeros to begin with. Let me finish the explanation. So I need to have an odd number of zeros to begin with. So I would have something like, you know, my parity transition here, and pushing x's for the zeros, and then exiting from the sort of odd part, right? So I exit from the odd part because, you know, this thing is allowing me to count the number of zeros. And the fact that I exit from here means that I'm ensuring that I have an odd number because I'm exiting from the odd parity. And then I would check, you know, so then I would epsilon transition, and then I would check that I have an odd number of ones, and in fact the same number of ones as zeros, right? And then the logic would be the same for the other part, for 1 even, 0 even. It's just that now, you know, I'm going to exit from the even part and then check that I have the same number of zeros as ones that I pushed, right? So I'm not going to do all of it. This is enough to give you the idea of what it should be in general. Yes, question? Yeah. Yes, yes. Thank you. Yeah. Thanks. Yeah. So notice the error, right? I just didn't update the base case here. Thanks very much. Okay, nice. So it's getting close to where I need to take a break. I will give you this one not as a solution, but more as an exercise for later. So this is going to be the last one before I take a break. So it's also going to be to classify a language, right? Except that the language is going to be W in AB star, where the number of A's is equal to 2 power the number of B's, right? So in this case, I'm just going to tell you that this is unlikely to be even context-free. So this is not going to be context-free. In general, when you have something like a power or a factorial, even just a multiplication, that's way too much for stack to handle. Stack is like this dummy memory, right? So it can't do much more than just count doing plus one. So it's kind of hard to see how you'd just use a +1 incrementer to do something like 2 to the power of something. So you know, a stack can only do something like +1s. It can't do something like, you know, take something and then duplicate it and then take it and then duplicate it again and so on, right? Because that's what really the power is. It's, you keep multiplying by 2. And so then you're going to need a pumping lemma argument for context-free languages. I will say one thing. I'm not going to solve it, but I will say that these types of questions where the string in the language is kind of free form, right? There's no restriction on what the form of the string should be. It's a lot easier if you actually do have a particular form. And to do that, what you can do is you can just intersect it with a regular language. So you can just say, you know, suppose L is context-free, then L prime, which is L intersect L of, let's see, B star, A star, right? This should also be context-free because context-free languages are closed under regular intersections, and this is a regular language, right? So then this means that Bn A power 2 to the n, which is, you know, just taking all of the strings in here and then just filtering the ones that have B's and then A's. This should also be context-free, right? But then you can show that this is not context-free via a pumping lemma argument. And this actually simplifies your cases a bit more. So I recommend this trick if it ever happens that you need it. Okay, cool. I'm going to take a break. Otherwise, I will collapse. So let's start again at 4:15. I should probably pause the recording.